Why are craters on the moon always round? Are there limits to the maximum size of a telescope? And can black holes have atmospheres? All these questions and more in The Question Show. It's time for The Question Show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Restoration Shaman, how big can a telescope get before diminishing returns? For a ground-based telescope, you have a bunch of issues that are going to start causing you problems with the size of your telescope. It's going to give you diminishing returns. So the first thing is the atmosphere, which is that until a couple of decades ago, there was really a limit to the size that you could use a telescope for, because at a certain point, the atmosphere causes so much distortion to the images that you're trying to capture that there's no value in attempting to do a longer exposure. It's just going to all turn into mush with the atmospheric distortion. And then they developed this technology called adaptive optics that essentially reverses the atmospheric distortion, and it acts like a ground, it's as if a ground-based telescope is in space. And so a lot of those problems have gone away. And so now telescopes can just get bigger and bigger and bigger. And we're seeing the development of the upcoming 39-meter extremely large telescope from the European Southern Observatory. And people had proposals for building 100-meter telescopes. So there's kind of no limit for optic size on the ground, but you do start to run into gravity. And so at a certain point, just the pull of gravity on the superstructure of the telescope just becomes such a pain. You're having to build more and more telescope to support the thing. And about 100 meters is sort of the largest feasible telescope that you can build on the surface of the Earth for a reasonable budget, $5 billion. And then beyond that, the thing is going to start just getting too difficult to wrangle. And also there are issues that you can solve with a smaller telescope, like with adaptive optics. But once you hit a certain size, then, you've got temperature changes, you've got all of these issues, and the metal is changing based on the amount of heat in the inside of the building and so on. And it's really hard to compensate over large scale. So I would say, beyond 100 meters, you start to get diminishing returns for sure. Once you go to space, though, a lot of those issues disappear. You no longer have the atmosphere. And so the size of your telescope can just get as big as it wants to be. You do have temperature changes. So those are going to start to become an issue, but you can adapt to them. You can have telescopes that are made of multiple segments. And so the multiple segments can move and change and adapt depending on, like there is a role for adaptive optics in space for dealing with temperature changes, as parts of it are being hit by the light of the sun, even if it's behind a sun shield. And you're going to want to be able to adapt your telescope shape to be able to handle that. But you could just go big. Like you could go 100 meters, 1,000 meters, kilometers across, and you would still have value for your telescope. Now, you would eventually start to have a problem where essentially, people always talk about this idea of interferometers. That if you take two telescopes, you separate them a certain distance apart, then the telescopes act like the separation between the two telescopes. And as long as you can align them down to the nanometer, down to the wavelengths of the light, and they're collecting the same wavelengths, then you can use that baseline, that difference between those telescopes. But a thing that most people don't realize is that any telescope is actually an interferometer. That if you have a single telescope mirror and you've got, one side of the telescope is collecting photons and the other side is collecting photons, you get the size of your telescope mirror because you're able to have them be arriving at the telescope at the same wavelength. But once your telescope gets too big, then you may get to a situation where photons are not arriving at the same wavelength on both sides of the telescope, and now it is kind of no longer in phase. And so you're going to have some issues as your telescope gets too big. But practically, we are talking huge. Now, for personal telescopes, the rule is always just, spend as much money as you can afford. right? That you will reach no practical limit when you try to buy a telescope. You want to get as much aperture as you can afford. If you can afford a 10-inch telescope, buy a 10-inch telescope. You can afford a 12-inch telescope, buy a 12-inch telescope. That aperture is the most important thing. Now, that's not entirely true because, portability is an issue. If you get a 20-inch telescope, then you're not going to have anywhere to put it inside your house. You're going to have a hard time moving it outside the house. You may have to keep it in a barn, but you're going to love the optics from a telescope that big. LL, are there any benefits to building an optical telescope on the moon? There are some benefits to building a telescope on the moon. There are a lot of downsides, like you're trying to put your telescope on the moon, and the moon is very far, and it is very expensive to put things onto the moon. Well, it might cost you $3,000 a kilogram to launch a mission into low Earth orbit. You're looking at millions of dollars to put a kilogram down onto the surface of the moon. But hopefully, over time, with more missions, the cost will come down in price. The moon is really good as a place for a radio telescope because you have no atmosphere. You can be on the far side of the moon. And so the moon itself is blocking all of the radio waves that are coming from the Earth. All of our earthly transmissions are being blocked. And so the moon will be radio quiet. And then you can, say, put a giant observatory, a radio telescope into a crater and follow the curvature of the crater to be able to now have this enormous telescope that's accessing the universe. And so a radio telescope is one idea that is considered. But there are some really great ideas for putting an optical telescope on the moon. And these ideas have been around for a long time. When James Webb was first designed back in the 90s, the ideas went back and forth was, are we going to build a big space telescope? Or maybe we're going to build a telescope and put it on the moon. And then eventually they settled on the current format for James Webb that we see today. And so one of the things that's really interesting about the moon is that you can put an interferometer on the moon. That's where you have multiple telescopes that are separated by distance, and then they can work like a telescope that is the size of the distance between those telescopes. And on Earth, you have to deal with the atmospheric haze. It's really hard to line things up to build this interferometer. Space-based interferometers are in the works, and people will eventually build these things. And you need a way to be able to maintain the distance of your separate telescopes as they're free floating in space. But on the moon, it's sort of the best of all worlds, which is that you don't have an atmosphere. And so you can set up your telescope. You don't need to build a complicated adaptive optic system. And then you can move your other telescope some distance away from the first one, and then you can line them up with a laser to get them perfectly in tune, and you can build an interferometer on this stable base of operations. The moon is mostly geologically stable. You're not going to get a lot of issues. They're going to change flexing, tides, things like that. And so you can separate these optical telescopes on the moon, bolt them into a foundation, and that is sort of considered to be one of the easier, cheapest ways that you can get an optical interferometer functioning. But you've got to get to the moon first, and that's going to be the challenge. Okay, Charles, cheap pockets. Could a black hole have an atmosphere? Sort of. Like when you think about an atmosphere around the Earth, the atmosphere is this layer of gas that surrounds planet Earth, and it is held down by the gravity, but the pressure of this gas and the temperature of it stops it from turning into a liquid or a solid. It wants to remain a gas. And so you get this shape of the atmosphere, this density and thickness of the atmosphere because of the Earth's gravity, but also the chemical characteristics of the gas. The sun is another good example. The sun has an atmosphere. You have particles that are whizzing around the sun. And even though the sun has an enormous amount of gravity that is pulling material into it, also those particles have a lot of energy, velocity. And so they are held out away from the sun, and they can form this atmosphere around the sun. And in fact, the corona, like when you see an eclipse, and when the moon passes perfectly in front of the sun, you can see these cool kind of petals that are around the sun, and that is the sun's atmosphere. And so a black hole will have a corona. It will have material that is surrounding the black hole. And a lot of times, when a black hole is actively feeding, it can't eat an entire planet, star, whatever. It actually breaks it up and tears it into this accretion disk that surrounds the black hole and whirls around it. And then these magnetic field lines are spinning around the black hole that are then sort of channeling material into these jets that go out of the north and south pole of the black hole. But you also get all of this hot gas that is surrounding the area that's glowing in the X-rays. And this is how astronomers find black holes in some cases, is they can see this essentially atmosphere, this cloud of plasma that is surrounding the black hole in its environment, caused by the intense magnetic field, the energetic particles that are around it that are blazing in X-ray radiation. And so, it wouldn't be a breathable atmosphere, but there's definitely a cloud of highly charged plasma around a black hole. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Do you want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who's already subscribed, and welcome to our recent newcomers: Sarav, Margie B, Scott, Peter, Paul Mackin, and Sheldon Heitman. Join the club at patreon.com/universetoday. Mr. Man, are all craters circular? Why don't meteors striking at an angle make elliptical craters? Yeah, if you look at the craters on the moon, they are all circles. And you would expect that the objects are coming in at a variety of different angles. So why are they all these nice, perfect circles? And that is because what happens is that when an object comes in and hits the moon at any angle, as soon as it hits the moon, the kinetic energy of the object, the impactor, is turned into energy. Essentially, it vaporizes. It's like a bomb that goes off on the surface of the moon. And then it creates this almost like a mushroom cloud in that spot that, the energy goes straight down, gouges out this big chunk of the moon, and you get this splashback of material. You get this ejecta blanket that comes out of the crater. And it doesn't really matter the angle, as the object is coming in at any angle, as soon as it touches, and it explodes. And that's what creates the crater, not the impact. But there are some examples of things that hit at such a low angle that they actually do create a bit of a smear of a crater. And so there's a couple of examples where they must have come in at 89 degrees, 89.5 degrees, like a really low angle, a very shallow angle, and you actually do get a bit of a smear of a crater. You also get examples where things have broken up, and you can see like a shotgun, like a line of craters that have all sort of lined up. TJ, will Starship successfully refuel in orbit in 2025? Podcast listeners, I made a I don't know face. Casey Ream, is there a consensus on how likely it is that these primordial black holes actually exist? There is no consensus. So we're at the place where scientists have proposed that conditions in the early universe were dense enough, and that you had these regions of overdensity and underdensity that were so different that you could have black holes just forming in situ, just right there in the early universe. And then those can be any size. You don't need the process of a collapsing star to form a black hole. You just get any size of black hole from something that is the mass of like I said, a house, an asteroid, a star, 1 billion times the mass of the sun. You could have all of this stuff forming right there in the beginning of the universe. And then one of the proposed ideas that this could be an explanation for dark matter. But the problem is that there should be some evidence for these primordial black holes, because as they pass in front of stars, they will be warping the starlight, and you would detect this microlensing event, and you would be able to see, if they're 10 times the mass of the Milky Way is made up of black holes, then there's a certain mass regime where so many of these are going to be out there that they would be easily detectable by watching as stars are flickering, as black holes are passing in front of them. And astronomers don't see that. Astronomers have done surveys to look for these black holes that are out there in vast numbers. And so they've been able to rule out various mass ranges for primordial black holes. Now you're left with some mass ranges that are either like 1,000 times the mass of the sun or more, because they would be very rare. Like you would occasionally see one of these pass in front of a star, but there wouldn't be a lot of them. If you added up these 1,000 times the mass of the sun versions, then you could come up with dark matter. Or they could be much lighter. They could be more like the mass of an asteroid. And then you wouldn't detect their microlensing events as they were passing, but there'd be a lot more of them out there. And so astronomers are continuing to come up with ways that you could check to see if these primordial black holes are out there. And there's been other ideas like, there could be a black hole that is orbiting around the solar system and there is no planet 9. There's actually a black hole, which, I don't think very many people think is a legitimate possibility. Or you could have black holes that are trapped inside of planets and they're causing excess heat in the planet that could be detectable. So, I think that if you ask most astrophysicists and people who research dark matter and you say, do you think that dark matter is made of black holes? They'll say, no, probably. It is probably not the most likely explanation for dark matter. And then if you say, well, can you rule it out? They'll say, no, they can't, right? Which is fine. That's how science works, is that there's going to be ideas that are not the one that is supported by the vast majority of the evidence, but is still there and it's not been ruled out yet. And that's awesome. That's totally fine. You just wait. You just wait for the evidence before you make up your mind. And I think like a lot of people, okay, this is about to turn into a rant, so buckle up. But I think that, a lot of people want some kind of certainty about things that we see in the universe. What is dark matter? What is dark energy? Why are we alone in the universe? And they want that certainty so bad. The most extreme version of that is where people think that UFOs are aliens, right? They're like, I saw light in the sky. I don't know what it is. Therefore, aliens. Case closed. It's aliens. And if you don't believe that it's aliens, you're a bad person and you're part of the cover up, right? Like you have to be okay to be in this space where you are uncertain about the answer and about the outcome, and that you're just enjoying the process of watching the evidence build, watching as new ideas, new research proposals, new missions are launched, which are going to attempt another crack at this problem. And I think like the classic example, the one that I find most frustrating, but also kind of hilarious, is when people roll their eyes and go, dark matter, lol, that's ridiculous. Scientists just came up with this thing so they could make their equations work. And like anybody who says that, like, tell me you don't understand the search for dark matter without telling me you don't understand the search for dark matter, right? Which is like that it is this series of observations, these careful observations that have made over time that have built this growing understanding that the universe is not as we perceive it. And that nobody ordered this, nobody asked for this, and yet this is the uncomfortable truth. And that whenever you find these things that are surprising and shocking and not expected and so on, then the resolution is not going to come quickly. It's going to take its time. And so with dark matter, with primordial black holes, with why there's more matter than antimatter in the universe, what is dark energy, how did galaxies form so quickly, what was here before the universe? These are the big questions, and we may not find out the answer in our lifetimes, but we will enjoy the journey. And if you're not entertained by the journey, then science might not be for you. All right, those were all the questions that we had in this episode. Thank you, everybody who asked your questions both in the YouTube comments as well as everybody who showed up for the live show. And the live show is 2 hours long and is many, many more questions. So there will be a notification for when the next live show is, but usually it's on Mondays at 5 p.m. somewhere in the world. All right, I'm going to talk about a new feature that we've added, but first I'd like to thank our patrons. A special thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bear Lake Roofing, David Giltonet, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Paul Robuck, Sean Sargent, Spiderswap.io, Stephen Fowler-Menley, Thomas L. Skadron, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons. All your support means the universe to us. As you probably know, we record the live question show. It's 2 hours long. And what we then do is go through and edit out and find a bunch of the questions that are going to serve for the 2 question shows that we publish here on the channel. And that adds up to about 40 minutes. So 2 episodes that are 20 minutes long. And then you're left with all of the other material. And we call that overtime. Previously, we had just been editing together that overtime segment and making that available to the patrons as a podcast. And I'm not sure why Anton did this, but now he's got a little more time on his hands or something, and he decided to make it a video and then even put B-roll and do some nice edits and transitions. And so when you go on to our Patreon channel and you want to be able to watch the overtime segments, it is another video now that you can subscribe to. But you do have to be a patron to be able to get access to that. But whatever is the minimum amount you want, you can get access to the additional, it's about 40 minutes long, patron overtime segment from the question show. All right, we're continuing to add more features to all of our offerings, so I'll keep you posted. We'll see you next time.